So next one is threshold reduction. So this is going to be what is the effect of threshold voltage in the operation of MOSFET. Whether the threshold voltage is going to increase or it is going to decrease with the channel length. So we are going to have a degradation in the output conductance beyond what is required for channel length modulation. So when you plot a function between, when you plot a graph between threshold voltage and channel length, it shows a decrease. As the channel length is going to decrease, the threshold voltage is also going to decrease. The reduction in threshold voltage will quickly turn on your device. So when you use zero point 0.5 micrometer device, the threshold reduction will be around 100 to 200 millivolt. Okay, and the current will be increasing enormously by factors of 10 to 1000. So just for a gap of zero point 0.5 micrometer reduction in your device length, the threshold voltage will reduce by zero point 0.1 to zero point 0.2 volt or 100 200 millivolt, which will maximize your current 10 times to 1000 times. So to reduce this peak channel field and that will mitigate high electric field, so we are going to go for a lightly doped drain in modern devices. So this much amount of current cannot be withstood by your device. So it will try to generate enormous amount of heat, and it is not going to be making your device operating in the safer region, right? So to reduce that, we generally go for another structure called as LDD. LDD is lighter doped drain that is going to be used in modern devices. So in some cases, the doping profile results in overcompensation in the sense that higher drain voltage actually increase the threshold over some range of drain voltage, which will decrease the threshold. So see, all these things are trial and error only. So some profile, if you use doping profile, when you increase the BDS, threshold voltage is increase. When you use some doping profile, when you increase VDS, the threshold voltage will decrease. So it all depends on what type of profile you are going to use for doping. So there is no clear hard and fast rule that for a given doping profile, your threshold voltage will always increase. No, it depends strongly on what doping profile we are going to use for the device. Additionally, PMOS devices do not have high field effects, but NMOS devices have because electrons saturate fast compared to holes. So in PMOS, the majority carries the holes, and NMOS, the majority carries the electrons, right? The electrons saturate to their velocity very much quick compared to that of holes. So the PMOS devices do not have all these high frequency effects, high field effects, as like your NMOS devices, which are completely made up of electrons. And MOS is a unipolar device, right? So it completely depends on only one charge carrier. So when you make a device completely out of holes, all the concepts, whatever we have studied, will not be applicable because holes are complete set of particles from electrons and all properties of holes are completely different. But when you go for fabrication of a device with NMOS device, so all these short channel regime, all these long channel approximation, what channel length you are going to use, what is the area, everything will come into picture. So you have to design the device accordingly, separately for a PMOS and separately for an NMOS device.